All right, so I've mentioned several times what we call the transition state, shown at the maximum of the reaction energy coordinate diagram. The transition state is an unisolable um, state of the reaction where new bonds are forming and bonds are being broken. So we like to show what we believe is occurring at the transition state by drawing in partially formed and partially broken bonds with dashes. So when we have our alkene reacting with HBr that we talked about at the beginning of the chapter, the first step is forming a new bond to hydrogen using the pi electrons. So we show a dash where the pi electrons used to be, a dash where the pi electrons are moving to the hydrogen, and a dash where the former bonding electrons from hydrogen to bromine are moving to bromine. And that gives us the first step of the reaction where we formed the carbocation. Oh yes, and you know, students always like to call it carbocation. It's carbocation. And I think they say carbocation just to mess with me, because it drives me crazy. It's carbocation. Okay, in the second step of the reaction, we had our electrophile, our carbocation. Let's label these nuke. Hydrogen is the electrophile. And then in the second step of the reaction, we have our carbocation as our electrophile. At the positively charged carbon, and the bromide is the nuke, the nucleophile. When we draw our transition state, we are showing what new bond is going to form. So in this case, we don't have any bonds breaking, but we have a new bond forming from carbon to bromine, and so we show a dash line for the new bond that's forming. And then we draw the final product. So in the transition states, we are drawing partially formed bonds, partially broken, partially formed, using dashes. Okay. Reaction energy coordinate diagram for each step of the reaction shown in slide 54. So the overall graph would actually connect graph A and graph B at the carbocation. So notice that graph A ends at the carbocation, graph B starts at the carbocation. For the overall energy, we would actually connect these if we were showing the complete reaction graph. Okay, so for the first step of the reaction, the reactants have a low energy. We have a high transition state energy to get to, and then that transition state ends at our first product, the carbocation. This is the product of the first half of the reaction. Our second reaction starts with the carbocation as the reactant. It has a small transition state energy and it goes to the product. The overall energy of reaction, if we were to draw the line over from reactant energy to product energy, you would see that the overall delta G is negative. So reactants have a higher energy than products. That means that delta G is negative. Delta G is less than 0. For the transition state energies, you can see that the transition state of the first step is greater than the transition state energy of the second step. So the first step is the rate limiting step because it has a higher transition state energy. Not because the transition state value is greater necessarily, but because the actual maximum of the graph is at the first transition state and not the second transition state. Now we could describe the reaction in terms of kinetically stable, and that we would compare the transition state energies for both steps. And we would say that because delta G is greater at step one is kinetically stable compared to step two. And we would say that step two is kinetically unstable compared to step one. Delta G transition state 1 is greater than delta G transition state 2. Okay, and then we can also talk about the thermodynamic stability of the two steps of the reaction. So in the first step of the reaction, the delta G from reactant to product is positive. So we go from reactant energy to product energy for the first half. This is delta G step 1. And so in this case, the reactant has a lower energy than the product. So this step is endothermic, endo. And in the second half of the reaction, the energy of the carbocation, the reactant for that step, is greater than the energy of the product. And so in this case, delta G is less than 0. So that is for step 2. It's exo. So that would mean that step 2 is thermodynamically stable compared to step 1. Okay, and so those are just some comparisons that you can make and that you will be asked to make. So here we're showing the overall energy diagram for the entire graph. So I told you we would just combine A and B into one graph, and that's what we've done on this page. The rate limiting step has its transition state at the highest point on the reaction graph. So the rate limiting step is the absolute maximum. That's how we would describe it in mathematical terms. You can see that the overall energy is negative, so that's the overall reaction is exothermic. You can see we have the intermediate, so this is the product at the intermediate step, and the reactant at the product at the intermediate step is the reactant for the second step of the reaction. Okay. What is a catalyst? We need to go back and remember that we learned this definition in Gen Chem. A catalyst provides a pathway for reaction with a lower energy barrier. So we have the same reactant energy and the same product energy are unchanged. Reactant and product energy are unchanged. But the transition state energy is lowered for a catalyst. Catalyst lowers transition state energy, which means the reaction can occur more quickly. Okay, so a catalyst does not change the starting point or the end point. It only changes the transition point. energy. Enzymes are all biological catalysts. What an enzyme does for us is to lower the energy of the transition state. Most biological catalysts are proteins, and we call those enzymes. Um, an enzyme does not have to be a protein. We actually have some enzymes that are made of RNA, but for the most part, enzymes are typically made from protein. And the reactant of a biological reaction, instead of being called a reactant, is called a substrate. So these are just terms that you're going to need to know for biochem, but you should also learn them now. The active site of an enzyme is the position at which the substrate binds, and the action of that binding to the enzyme is said to put it causes the substrate to go into a structure that approximates the transition state structure. And the way that the enzyme interacts with the molecule is to form intermolecular interactions with the substrate so that it is more stably located at the active site. So you can see that we're showing hydrogen bonding between the enzyme and several of the groups on this sphingoglyco. It's a sugar which has amine groups. The enzyme side chains bind the substrate using hydrogen bonds on dispersion forces and dipole-dipole interactions. These interactions result in a change in shape of the substrate that approximates activation or the transition state structure, and that allows the reaction to occur more quickly. And some enzyme side chains actually interact with the reactant using acid and base reactions or nucleophilic reactions. We'll talk about that in biochem, don't worry about it now. And that's the end of chapter 5. We're going to start chapter 6 next.